This is Unit 8, Video 12. In this third video about acids and bases, we will dive into the reactions between acids and bases. We've talked about each separately, and now you can obviously put them together. And the products of an acid and base reaction are famous for being salt and water. So it's interesting because you have very strong substances, very corrosive substances. So hydrochloric acid here, the muriatic acid. Here you have sodium hydroxide, the lye of the base world, very, very strong, dangerous. But when you put the two together, you get good old table salt and H2O. And this is called the neutralization reaction, as we'll see. And if you use indicator, so this is actually using an indicator, and the indicator is universal indicator. It's red in an acid, blue in a base, and then turns green when the two are mixed. So these colors can actually be seen using an indicator. You can actually perform this reaction and pour the two together and get a beautiful green color, which means you're safe and you are neutral. So we're going to recall how to write these equations. So the neutralization reaction, in a little more detail, the cation from the base, so from sodium hydroxide, for example, it'd be sodium, and the anion from the acid, so hydrochloric acid would be chloride, will form the salt, so you have sodium chloride. And then what's left from the sodium was the OH, from the chloride was the H+. Well, these two parts, H+ and OH, actually are two components of water. Together, they form H2O. So technically, H2O can actually be split up into an acid and into a base. The HOH of water can actually be split up this way into these two components. And the molecular equation, if you recall, is the equation that shows the full substances, the undissociated substances, so just the regular way. The way we've done this is we consider this to be a double replacement reaction. And the double replacement reaction just simply replaced hydrogen with sodium. The first two elements replaced one another, and you got yourself sodium chloride. That's how you obtain this salt. And then you get yourself HOH, which is what water becomes. Now, if you split this up into a net ionic equation, and remember, net ionic equation considers only the substances that are reacting. So the spectator ion, in this case, would be sodium, and chlorine become the spectator ions. And the spectator ions, so these are spectator, then get canceled out, and we form a net ionic equation, which just shows the hydrogen and the hydroxide reacting to form H2O. And this is the essence of an acid-base reaction, forming water. So we'll do a few of these here. In fact, let's dive right in. Let's write a balanced molecular equation for the reaction of sulfuric acid with potassium hydroxide. So this is a molecular equation, so not net ionic yet, just the full substances. We'll do the molecular equation. You have to be able to write these formulas. So sulfuric acid is based on sulfate, which is SO4, which means we need two hydrogens to balance SO4 since it has a -2 charge. Potassium hydroxide is good old KOH. So consider this to be a double replacement reaction again. The hydrogen and the potassium essentially swap places. And you get yourself the salt, potassium sulfate. Now make sure you write it as K2SO4 because potassium has a +1 charge, sulfate has a -2 charge. So as a reminder, what we're doing anytime we're writing a salt, an ionic compound, we have to balance the charges. And since K is +1, you need two of them to balance the sulfate, potassium sulfate. And good old HOH or H2O. So make sure you balance the equation before you leave it. And it looks like we need two potassiums on the left, which gets us two oxygens on the right. And we have a sulfate, four hydrogens. We are balanced. So if you would like to write the state symbols for the reaction, let's go ahead and write the state symbols. The sulfuric acid in all acids will be aqueous. In this case, the base, if it's soluble, which it is, will be aqueous. The salt, according to the solubility rules, is still aqueous because all group 1 metal ions dissolve, and then water obviously is a liquid. So this is a case where 3 aqueous form a liquid product. Let's do the same thing now, except let's follow it up with a net ionic equation. So in this case, we're going to write the neutralization reaction between nitric acid and sodium hydroxide. So nitric acid and sodium hydroxide. Let's write the full equation first before we get to the net ionic. So nitric acid is based on nitrate, NO3, which has a -1 charge, which means you just need one hydrogen with it. Sodium hydroxide is good old NaOH. and then this forms the salt and water. H and Na swap places. You get sodium nitrate and water. You'll always get water as the other product in this type of acid-base reaction. Now, to get to then an ionic equation, remember what we did is we split everything up. And we split it up based on the fact that it was an electrolyte. So if it's a strong acid, for example, it was a strong electrolyte. And if it's an ionic, it was a strong electrolyte. And if it's soluble, like in this case, it's a strong electrolyte, this would be the liquid. So these state symbols, if it's aqueous, we went ahead and split it up. Now, this is true as long as you have a strong acid, because strong acids by definition split up. So the HNO3 will split up. But realize that if you had something like HF, technically that would not split up. So you would not write a net ionic equation for HF. That's the idea. Or it would actually be different. You would, but it'll be slightly different. But in this case, the H plus splits up from the NO3 minus. The sodium splits up from the hydroxide. On the right side, sodium splits up from the nitrate, and these again split up because they dissociate in solution. That's kind of the definition of how they exist in solution. Water does not split up. And then at this point, what we did is we canceled everything out that looked the same on both sides, which included the sodium and included the nitrate. And what we're left with is what we saw earlier, H plus OH minus to give you H2O. And this is essentially the net ionic equation. Now, to show you, let me show you quickly what would happen if it were HF. HF would actually not dissociate, so HF would stay together because it's a weak acid. Weak acids don't dissociate. The sodium hydroxide would still dissociate because it is a strong base, so that would dissociate. Now, in the case of HF, you'd form NaF for the product, in that case, NaF, which is soluble because it's got a group 1 metal ion, so that would dissociate. So you get yourself Na plus F minus, and then obviously you'd form water. In this case, what would happen, because HF was a weak acid and it did not dissociate, we don't cancel out the F minus. We only cancel out the Na plus. Your net ionic equation would have HF, the undissociated acid, reacting with the OH minus, if you got a little minus there, like so, to form F minus and H2O. So these would be the four products of a weak acid, an undissociated weak acid, and that's essentially the difference. Okay, let's finish up the discussion of another reaction between acids and bases, and that's between carbonates. Carbonates, we said, are bases, and carbonates contain the polyatomic ion carbonate, CO3. And if you react CO3 with an acid, it releases carbon dioxide gas. It's interesting because you're undoing what nature did, many years ago, or recently, if it's a mollusk of some sort that got formed in the ocean. But the CO2 got trapped, and these animals actually, usually the carbonates are animals that incorporated CO2 in their shells, and then that became carbonate. So this is an ancient reaction that produced carbonates from carbon dioxide. And you can release that ancient creature into the air by adding an acid to it. So here's what happens. The acid reacts with a carbonate to produce the salt. So here you have the salt. Kind of what we're used to, an acid and a base forming a salt. You still form a salt. You still form water. Notice the acid and the base form salt and water. But in this case, you also form carbon dioxide gas, and that's the difference. Now, the way to remember this, here it says, you can think of the intermediate product as being carbonic acid, H2CO3. And the way to think about this is if you double replace these two, your product technically would be NaCl, you can see that, but then it would be H2CO3. So you can think of H2CO3 as the intermediate product. And obviously the other product then is NaCl. So this could be the intermediate products. The NaCl stays, that's your salt, and then H2CO3 actually breaks apart into water and carbon dioxide. So that's, if you want to think of it that way. And this is, if you recall, a famous reaction where if you have a nonmetal oxide added to water, you produce an acid. So this is the breaking down of an acid back into a nonmetal oxide and water. A similar thing can happen if you have sulfates. You can actually give an analogous reaction with sulfates. So say if you had sodium sulfate, or with a phosphate, you can actually get a similar reaction. And the most famous version of acid with a carbonate is good old vinegar and baking soda to produce some CO2 gas. It's a famous science experiment we can do at home, and it actually releases the carbon dioxide into the air, and for the future critters to absorb and react. Alright, so let's try this. Let's try one reaction. Write the molecular equation for the reaction of nitric acid and calcium carbonate. So again, we have nitric acid, which is HNO3, and then we have calcium carbonate, CaCO3. So when we react these two, we technically get ourselves salt, water, and carbon dioxide. Now the salt that we'll get has to be the calcium nitric salt. So the salt will be the cation from the base and the anion from the acid. That's where the salt comes from. So we get calcium nitrate. Be careful, calcium nitrate calcium has a +2 charge, and nitrate has a -1 charge. So we need 2 nitrates down here. Then we get water, obviously, H2O, and then we get CO2, carbon dioxide gas. And that's really how it works. Now, to make sure it's balanced, it looks like we need 2 nitrates on the left, since we have 2 of them on the right, so double that. That gets us 2 hydrogens, and that's 2 hydrogens from water. So it's actually a pretty simple equation to balance. Now, if you were to write a net ionic equation for this, because nitric acid is strong, it will dissociate. A calcium carbonate is actually a solid in this case. So it's a solid, it's because it's insoluble. Many carbonates are solids. And so what you would do is the nitrate would actually be the only thing that cancels out in the net ionic equation. Everything else would stay. So technically your net ionic equation will look like this. H+ reacts with calcium carbonate to form calcium 2+, water, and carbon dioxide gas. And this is actually a reaction that is a test for a certain type of rock called limestone. This is actually limestone. What you could do is you go out into the field with your little container of HCl. This would be HCl. Usually you do 0.1 molar. You have to have a pretty small molarity HCl to get this. And here you have your rock sample, and you put a few drops on your rock, and if the rock fizzes, if all of a sudden, let's make it red, if all of a sudden it begins fizzing and releasing CO2 gas into the atmosphere, you know you have yourself limestone. If it does not fizz, you have some sort of other rock formation, maybe dolomite, maybe sandstone, maybe chert, maybe who knows what you've got. Alright, so this is a famous reaction, an important one for you to know, the reaction between an acid and a carbonate. This wraps up the video for us, and we'll get into more concepts of acids and bases in future videos.